All right, hello and welcome to this video that begins our series where we will be talking about the different equipment that you need to have on your workbench and how to use those equipment once you've acquired them. And in today's video, we are going to talk about none but the almighty oscilloscope. This is a device that is set to make other engineers in fields other than electronics envy us because we have such a powerful visualization tool. And what this guy does is basically to help you to visualize the variation of voltage with respect to time. And as you would agree with me, in any electronics circuit, it's mostly when voltage or current is changing with respect to time that interesting things are happening in the circuit. So I'm going to start by talking to you about some of the features you need to consider when choosing your scope, and then we will do a few experiments with it to learn how to basically use it. Mine here is a Siglent SDS1104XE. The first thing you want to check when acquiring a scope is basically the maximum frequency that it can sense. Mine can sense up to 100 megahertz. There are some that goes to 200 and even more. And so you have to choose based on the level of work you'll be doing, the kind of work you'll be doing, and what you think is the maximum frequencies that you would have to be sensing. For example, if you are working on RF circuits, radio circuits, then this feature or this specification becomes super important for you to consider. Another thing you also want to consider is the samples per second. So mine can do 1 gigasamples per second, and what this means is that in a second it can take 1 billion readings of a voltage at a particular point to help it to plot it properly for you. Then the next thing you also want to look at is how many channels it has. Mine has 4 channels right here. So what it means is that I can be sensing 4 different voltages with respect to time at the same time. So at the very least, I would suggest you go for a scope that has a minimum of 2 channels so that you can probe your input and also probe your output, and that is going to help you to know what the circuit is doing. So what is happening in between the input and the output as far as your circuit is concerned. Now, I'm going to talk to you first of all about the most important part of it. It is called the probe. Okay, not the most important part, but a very important part of it. It is called the probe. And I'm trying to see if I can get the camera to lock in, but you can also trust what I'm saying. So I think I'm struggling to see it here, but if you take the probe of a scope, you can see there's a part it is written 1x and there's a part it is written 10x. Well, it depends on the kind of probe you have, because some will not be 1x and 10x, some could even be 10x to 100x, or it could be variable in between, right? Now what happens is the probe comes with 2 tips. The first one is this one that is very short and runs to the body of the probe that you hold in your hand. This is for the ground connection. So whatever is the common point in your circuit, that is where you hook up this guy. And then when you pull this onto yourself, you see this tip appearing here. That is where you will hook. So I'm trying to see if you can lock in on this. Yeah, so this is where you hook to the point in your circuit where you are interested in measuring the variation of voltage with respect to time. One thing I would like to mention is that this is a digital oscilloscope. There are analog ones that are the most real time. The reason the digital ones are not actually real time, and I'm not saying this to say they are bad, they actually do have lots of advantages over the analog ones. I'm saying the digital ones are not actually real time because, for example, it samples, right? It takes 1 billion samples per second, and it can do some processing before actually rendering the graph here. Now, at the expense of losing that few, maybe nanoseconds or picoseconds in terms of real time, the processor in here is able to perform a lot of things on the signals before rendering them. So you can do some mathematics and stuff, which are things that will be difficult for you to do automatically on an analog scope. Okay, now we've spoken about the probe. I need to mention that there's 1x, 10x, or whatever x you see there. It determines the level of attenuation that the probe does to the voltage it is sensing before it sends it to the processor in here. So an oscilloscope is basically a probe sensing some voltage, okay? It also has the ability to do DC or AC coupling. So if you have a signal that is a mixture of DC and AC, you can tell that the probe to block DC and only pass AC, or to allow both DC and AC. This is what is known as coupling, and we can see all of that on the screen. So the settings here determines the level of attenuation that it does on the voltage before sending it for graphing on the screen. Now we have spoken about the probe. One last thing. So let's say if I put it in 10x and I hook this point up to a 10 volt, what this guy will report, what the probe will report to the processor in the scope is actually 1 volt. So it will attenuate it by 10 times. So it will report 1/10 of it. And this becomes important when you are dealing with high voltage stuff. Okay. Now let's keep our attention on the screen here. You can see there is a grid on the screen, and this looks just like your normal graph sheet. And because you are visualizing the variation of voltage with time, time is the independent axis and voltage is the dependent axis. So voltage is plotted on the vertical and time is plotted on the horizontal. Over here are buttons that helps you to choose which of the channels you are controlling at a particular point in time. At this moment, I have a probe hooked only to channel 1, and so I have turned on channel 1. I can actually turn it off like this, and then it's gone. So to turn a particular channel on, you just have to press the number that identifies the particular channel, and they are also color coded. So if I press channel 2, for example, you can see it's a big pinkish bluish, and then channel 3, and then channel 4, and you can hook the probes up and connect them to different points in your circuit. I am not interested in any of these channels apart from channel 1, so I can turn this off and then leave just channel 1 on. And like I mentioned, when you adjust the attenuation level on your probe, like I showed you here, mine is 1x, 10x, you have to select on the screen and make sure that it is matching whatever you have set your probe to. So you can see that there are attenuation levels from 0.1x all the way to 100x. And so this is also something you want to consider when you are buying your probes. Look at the attenuation levels that they support, and always make sure that whatever you have set on the probe itself matches the settings that you set on the screen. Okay, so if let's say my probe is set to 10x and I come to set it to 50x right here, whatever is plotted is going to be wrong for you. So always make sure that these settings do match. Mine is 10x. If I put it at 1x, then I will also change it to 1x. Now, everything you are learning here applies to every other scope regardless of the manufacturer. And this is one thing I have seen about scope manufacturers, is that the interface can look intimidating at first, but once you learn how to use one scope, you have actually learned transferable skills that you can take to other scope manufacturers. Of course, the buttons might not be located in the exact same places, but the functionalities are almost always the same. So these buttons here helps you to control the vertical scale, what happens on the vertical scale, and you can see that it has been labeled nicely on the interface. So I can use this to adjust my volt per division. What it basically means, like at this moment I have set mine to 1 volt per division. So what it means is that if I read between one grid, like the bottom of one grid, let's say I start from here, the bottom of this grid to the top of this grid, if a line is drawn here, that line is representing 1 volt. That is the volt per division, and it can go all the way to whatever maximum is allowed. Mine can go all the way to 100 volts per division. So if I put it at 100 volt per division, and let's say I move my zero line to the down here, and a line is drawn here, it means I'm measuring 300 volts. So you just have to be sure you know how to read where the line is based on your volt per division. 100 volt per division is too much for what we are going to do today, so I'm just going to leave it at 1 volt per division. And there is also the ability, like I said, for you to move the 0 point. So the yellow line here represents channel 1, and then you can actually change the 0 point for each of the channels. So I select that this should represent my 0 line. So this is 0 volt, and then this is going to be 1 volt because it's 1 volt per division, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, and 7 volt. So you can move the 0 point depending on the magnitude of voltage that you are measuring. And as always, you can press the middle for it to go back to the default. On the right side here, we have the controls and the knobs that we use to control the horizontal scale, which is the time. And this is very important because it also determines how long it takes for the scope to also be sensing or acquire data or voltage readings from the point that you have connected it. Okay, now one other very important thing that confuses a lot of people is the trigger settings, and I'm going to spend some time to explain this to you. So the trigger settings is basically how you tell the screen to refresh. You control the refresh rate of the screen. If I press setup, for example, it means I'm going to set up some triggering. At the moment, you have to choose the trigger type, okay? I mean, at the moment, I can see my trigger point is down here because I know how to use the scope. But for you who is learning, I'm going to explain everything. So you choose the type, okay? You can trigger on an edge, on a slope, on a pulse, on a video, on a window, on an interval, dropout, rand pattern. We can't go through all of these in one video. I'm going to just spend time on the edge triggering. So I'm going to choose edge like this. Okay, so you press these buttons down here are menu aware, they are context aware. So what they do depends on the menu or the functionality you are trying to configure. So I use this to scroll up and down if it's scrollable. So, and then to select, you just press it. So I have selected that this is triggering on an edge. And then now you have to also choose the channel on which you want the triggering to happen. At the moment, I only have channel 1 connected, so I leave it at channel 1. And then there is also the slope. This is how you determine when the screen should be refreshed. So it all depends on what you are doing. That is why it is wrong for you to just power on a scope, hook up the probe, and expect to see things. I bet you wouldn't see things as you expect them to see. And most of the time it has to do with the trigger settings. You might have a trigger setting that is basically making your scope not even pay attention to what you are interested in observing. For example, right now my trigger point is all the way down here, -45, and I'm saying I want it to trigger on a rising edge because this is an edge detection, and I say on a rising edge. So if it's on a rising edge, then my level should be somewhere above the 0 line. So what I'm telling the scope is that whenever the voltage crosses this particular line, I want you to keep sensing and refreshing the screen for me. So if it's rising edge and I put it all the way to negative 4.5, nothing interesting is going to happen. So to do that, there is a special button you use to control, and it belongs in the trigger settings. So you don't, at this point, you don't use this one here, you use this one. So you can see that as I change it, observe the value where I have put the pen. You can see that it's also changing, right? So I can bring it all the way to, let's say, 0 or something above it. I mean, you can always, it depends on what you want to do, but for this, I just want to put it at 0. Or I could also, I believe, just have pressed the middle. So let's say it's down here. If I press here, it comes all the way to 0. So you have to experiment with whatever scope you are using to also know what it is doing, right? So we've spoken about how to enable, disable the different channels. We've spoken about how to control the vertical scale. We've spoken about how to control the horizontal scale. Basically has to do with the timing. And then I have said a bit about triggering. We will spend some time on triggering a lot more, okay? Now, I'm going to hook the scope up. Always remember, this goes to negative and then this goes to positive, or whichever point you are interested in observing the voltage at. You can actually also push this one out and then you will be doing some point sensing, okay? I don't know which scope you would buy or which scope you have currently, either in your school lab or at home or at work, but many scopes come with signal source, at least one signal source that you use for calibration. Mine happens to be here, so I'm going to hook, and you have to also match it. There's a ground symbol where you're supposed to hook the ground, and then there is the other pin where you are supposed to hook whatever you want to sense. Now, you can see that something is obviously happening on the screen, but it doesn't make sense. This is why you have the ability to adjust your time scale. Okay, now because I adjusted the time scale, it's becoming clear to me that this is a square wave. So if it is all squished together, it means my time scale is so small and it has to squish everything because the screen real estate is limited, right? And it's scrolling away. So I can just increase. It doesn't change the signal you are measuring, it's only changing the presentation. And over here, you can see it's scrolling anyhow. I can just move my trigger point, and then now you can see that it is not scrolling. Does this mean it is not measuring? Yes, it is measuring, but the rate at which it refreshes the screen is what I have changed. So I have moved my trigger setting to 1.22 volt, and look at it. I said it is a type edge, okay? It triggers on an edge on channel 1, and it's a rising slope. So I say when it sees the signal rising and it gets to 1.22 and above, it should refresh. So this triangle here is telling you where your trigger point is, and this is the reason why when I bring it all the way down to 0, okay, this has gone to the middle. When I bring it all the way down to 0, you can see that it's moving because, like, yes, it's crossing the 0 a lot of times and it has to keep refreshing. So all of these are things you have to play with, right? But like always, if you hook up to a source that you have no knowledge about, like you've hooked up your probe to a source and you have no knowledge about what kind of signal is coming from the source, it will be hard for you to adjust your vertical and horizontal scale to something that makes sense so that that signal is presented nicely. Every scope, and I mean every scope, has a button called auto setup. It might not be placed here, but you definitely find it somewhere on your interface. Just press auto setup. And what this makes your scope do is the scope is going to take a few samples of the signal that is coming in, and then it will determine what are the appropriate vertical scale setting, horizontal scale setting, and also trigger point that is going to help it to present it nicely for you. So you can see at the moment that the scope did more than two things, or actually even three things. It first of all moved the zero line of the vertical axis down here. So usually it's supposed to be at the center. It has moved it all the way down here because it feels this is going to give it enough screen real estate to present it nicely to me, right? So if I want to take control from here on, I have pressed the position button to reset it. So I have moved my zero point here again. And then it also set the volt per division to 500 millivolts per division. I might not want it that way, so I am increasing it a bit. Okay, now I have set it to 1 volt per division. And then my trigger source, I like where it is, but if not, then I can always bring it down so that it can begin to scroll, or you move it wherever you think is important enough for you. Like if you move it out of here, it achieves the same purpose. So try to understand what is triggering and know that triggering is basically you telling the scope when it should refresh the screen. Very, very important because it is the number one source of frustration for people. Okay, now that we have a signal running through the scope, what are some of the things we can do that we don't have to do manually? Well, there is this math thing here, and it helps you to do a couple of perform mathematical operations on the scale, or on the signal that you are reading on a particular channel. So you first of all have to choose the operator. So let's say I want to calculate the integral of my signal, right? You don't have to do it manually. You just have to select, and then you can also select the source. It can actually even help you. Let's say I had channel 2 also connected to some signal, and I want to see what is going to be the result of adding the signal on channel 1 to the signal on channel 2. You can do all those things. So you basically just press the math button, and then you can choose what to do. So if I want the square root of my signal, this is the square root of the signal that is coming in. Okay, now I've put the mathematics thingy off. The kind of mathematical operations my scope performs might be different from what your scope performs, but always look for the math button before you pull a paper and pen to do mathematics on your own. This thing is a computer. It has a processor. Let processors do what they are good at doing, and humans do what humans are good at doing. All right, what other thing can we do? We can take some measurements. So to do that, you press the measure button. Again, it's on every scope, and then you have to choose the source. Again, I only have channel 1 enabled, and then you have to choose the type of measurement that you want. My scope allows me to choose types of measurement that I want. So I can actually measure the square root of peak to peak. I can measure the maximum, which is the highest point. And when you select, right, the scope is going to tell you what this particular measurement does. So it says maximum, it measures the highest value in a waveform. Minimum, so the names even make sense, right? They are descriptive. There is the amplitude, there's a top, there's a base. At the very least, you might be interested in something like the frequency, which has already been selected. So sorry, here I said square root. It's not. It's only a check mark that is indicating that I've selected that it should measure the peak to peak voltage. I can also measure the frequency, right? And a lot more. I can measure duty cycle, the rise time, the fall time, and whatnot. If you want all measurement, again, your scope also is going to allow you. If I press all measurement on, then as it is sensing the voltage with respect to time, it is also performing the calculations that are needed so that it can report the accurate values for all the measurements that you are interested in. So at the start, when I mentioned that this is a digital scope and so it is not really real time as you would have it in an analog scope, and I mentioned that, but it does have some advantages. These are some of the advantages. The fact that the probe senses and the processor in here does some processing before it does the presentation gives it some window of time to do all of these magic that isn't possible on an analog scope, right? So I'm going to put off this measure button, and then again, it's not only for measuring it's not only for measuring signals that change with respect to time. Even if your signal doesn't change with respect to time, it's going to be a constant signal, constant voltage, right? So I have on my workbench here a power supply. I'm not going to show that because we will have a separate video on every equipment that is in my lab, but I'm going to hook the negative pad to the negative side, the common of my power supply, and I'm going to hook the tip of the probe to the positive, and my line is gone off screen. What this basically means is that I'm measuring some voltage that is higher than my volt per division. So what do? I increase my volt per division, and boom, now I can see whatever it is that I am measuring. If this is 2 volt per division and this is my 0 line, this is 1, so that is 2, and then another grid here, so 2 times 2 is 4, and this is midway between the third grid, so that is 2, 2, and then midway of 2 is 1, so I am actually measuring 5 volts. The question is there a way by which this guy can tell me what it is actually measuring? Yes, I just showed you, and there are other ways as well. So if I come here and I ask it to measure everything, I look at the max because it's a constant voltage source. The max is 5.04, and I've actually set my power supply to 5 point something, so it is reading 5.04. If I increase the voltage on my power supply, you can see that it's also increasing. So I'm bringing my power supply all the way to, let's say, let me bring it to 3 volts. So my power supply is now at 3 volts, and you can see that this is also changing. So that's the beauty of it. As I move the knob of my power supply, you can see that in almost near real time, the screen is also updating to reflect what I'm doing on my power supply. And this is the beauty of a scope, right? So you saw how we can use the measure screen here to do stuff. There is another thing called cursors, and it helps you to zoom in at a particular section or portion of the graph, and it's basically either doing dy dx. It's either doing dy, like the change in y, which is going to be your voltage, or it's doing a change in x, which is going to be the change in time. For this particular one, I am interested in measuring the voltage that I'm reading. Yes, we all know we could press the measure button here and then it's going to do the same thing for us, but we can also do it manually. When you press the cursor, you choose the mode. So manual mode, it means you can move the cursors on your own, but I don't want the cursors vertical points to the x-axis, and I'm not interested in changing time. But you can see that it's basically telling me that this is my starting, this is the ending, and it will give me the difference between them to be 3.5 milliseconds. I am interested in the voltage. So what do? You change the type to Y. You can actually also do X and Y. So if I change the type to Y, then I can choose my Y1, and as I move this, you can see that it is also moving. I'll move it all the way to the 0th line. Hopefully I got it right. Yeah, it's 0.08. I want it to be 0. Yeah. And then now I can also choose my y2. I can choose my y2, which should be somewhere. Okay, it's here. So I'm going to move it all the way to the line. All the way to the line. You know, when it gets into the line, it's hard to see. So I'm moving it just right here. And then on this screen, it is telling me what is the difference between the first cursor and the second cursor, and that is going to give me the voltage, because I put the first cursor on line 0 volt and I put the last cursor right on the voltage level that I want to read. So if you don't want to do the math by looking at the voltage per division to sum up, which is easy to do anyway, so reserve these cursor stuff for more complex signals. And that's basically. So like I said, there are a lot of buttons on a scope and we cannot cover all of them today, so I'll do other videos that will show you the nitty-gritty details of these other buttons. But with what you have learned now, you will be able to use the probe to probe around. So I have a very simple experiment that I want us to do. Now I have this circuit here. Okay, what this circuit is supposed to do is it's just a switch, right? On top here is my positive rail, as you can see, and on top here is my negative rail. And so this is a switch. I think this is a 10k resistor. So I have literally pulled the switch up. So what it means is that if I put in, let's say, 5 volts between these two wires here, without pressing the button, if I probe this tip, I should read 5 volt because it's a pull up resistor here. So I should read 5 volt. Then what it means is when I press the button, it has to pull the voltage here to ground. So I can connect this side to a microcontroller and write code to read this particular line. And if this line goes low, then it means the button has been pressed, and so the microcontroller has to respond. Let's see if we can see that on a scope, and also possibly see what are some of the problems with mechanical switches like this. So I'm just going to put this on my workbench. Maybe you won't see it, but you've already seen this. It's a very simple setup, right? So I'm going to hook my power supply to it. Power supply. So let me put my power supply to 5 volts. Awesome. And I will hook the 5 volt to the top rail. I will hook the negative to the negative rail, and then I'll bring in my probe. I think I have to make you see this. So I'm connecting my probe ground to ground, and then I'm connecting the tip of my probe here. All right, let's let the cursors go away. All right, so let me hold this properly so you can see. Yeah, so this is my 5 volt, this is my ground, and my probe is hooked to the output because I want to see the output when this button has not been pressed. And so the ground comes to the ground. They have to share a common ground, so your scope has to share a ground with the ground of the circuit you are measuring. And then my point of interest is what happens at this point of the switch when I press the button. And like I said, it's a pull up arrangement, right? This 10k resistor here pulls it up to 5 volt. So if I have not pressed this, it should read 5 volt. If I press, it should come down. Now I'm going to put it on the table so that it is settled and there's no fluctuations in there. And then now see, when I press the button, it comes down. I release, it goes up. I press, it comes down. I release, it goes up. So this is exactly how it works when you hook it up to a microcontroller, that when the microcontroller senses the output pin and is low, it means the button has been pressed. And if I release it, it goes up. Now, there is something interesting that happens with buttons. It's called bouncing. Different manufacturers make push buttons that have either try to solve this properly or not, but you are rest assured that it can almost always happen. It's called bouncing. You see, the switch has it's a mechanical device. There's a spring in there, so when you exert force to push it, it can make contact multiple times before it settles. And to you as a human being, it feels like, yeah, I pressed it once and that was it. Yeah, I pressed it once and that was it. But if you are processing, like to the processor or microcontroller that is reading the output pin several times per second, it can actually see the fluctuations, and that will be a problem for the microcontroller. Let's see if we can set triggers to catch some of these things. All right, so now I want to see if it's possible for us to see the bouncing effect of a switch. It's sometimes hard to see, especially this particular button is a high quality one, but nonetheless, it doesn't fix it 100%. So there are chances that we can see that. So I come to my setup here, and then I choose the type. It is already at edge, but I'm doing all these so that it sinks in. And then my source is source 1, channel 1. Now the slope is rising. No, my setup is such that when I haven't done anything, it is already high. It is 5 volt here. So I want a slope falling. That is, when somebody presses the button, I'm interested in knowing when the output is falling. And because it's 5 volt, I'm interested when it crosses, let's say, the 2.5 level. So then I will use this button to set my trigger point. So again, pay attention to the number here, or this one here. That is what sets the trigger level. So I'm interested when it comes, let's say, all the way to 2.5, or anywhere below 2.5. Even 3 is okay. In fact, anywhere below 5 is what you are looking for, right? But I will just set it to, let's say, 2.5. Yeah, this is okay. It doesn't really matter. So this is where I want it to trigger. Then I'll be pressing. You saw some pass right away. You see, it happened again. You can see at a point. So let me put this one here. You can see at you see that it's not all the time that when you press it settles. It passed by. It's not all the time that when you press it settles. Sometimes it bounces back and forth. Now it's in auto mode. So in auto, the scope is waiting for the event to happen, but if the event hasn't happened, it will still be reading anyway. And then there is a single mode. I'll also talk about the normal mode one time. So there's a single mode. The single mode is such that the scope has sort of become a policeman. It is sitting there waiting for the trigger event to happen before it begins to read. Okay, so if I press now, then it tells me, okay, this is what I captured. So basically, I pressed, which brought it down. I brought it down, and then when I released, it went up again. If we look closely, or if we do our time settings correctly, we might be able to catch a switch bounce. Like I said, it doesn't always happen, so chances are that it won't happen. If it's in single mode, you always have to go to single mode to let it re-trigger again. But maybe we can play with this signal and see. So if we look critically at this signal, I think this is good enough. If we look critically at this signal, you can see that the bouncing didn't only happen when I press, sometimes also when you release, because at this point I had released it, so it has to move from 0 volt to 5 volt. But look at it, it sort of moves a little above 0 volt sometimes, and then it came back to 0 volt, and then it went up. So to a microcontroller, it sees all these and it will respond to them. Imagine you have coded your microcontroller that when this thing is down to 0 volt, it should do something. Then what does it do in between 0 and 5 volt? This is the problem that is known as switch bouncing, and that is why there are techniques for switch debouncing. I want us to play with it a couple of times to see if we can actually catch this properly. So where is my time scale? Let's go to milliseconds. I think some milliseconds should help. Micro seems to be too fast. Is 1 micro enough? So if I press this, and then so it has captured something. Let me zoom in. Yes, but you can even see that the rising itself is not instantaneous. Look at it. Look at how it rises. You can see that it's not instant, right? So, and again, remember, your microcontroller sees this. It sees all the time when the thing is rising between here, and here, and so it's a problem. And that is why we do debouncing. I'm not going to talk about debouncing, but if you have followed my Zephyr tutorials, then you should know about debouncing. I still want to try and see if we can get a proper view of let me increase my time and see. It's not doing any good. Yes, this is beautiful. So look at it right here. So this is also why it is important to have your time scale and your voltage scale set properly. You see, if my time scale makes it squish together, everything looks so perfect. It looks so perfect, but the devil is in the details. As I reduce my time scale, and this is also why it is important that this digital scope is able to take 1 billion samples per second. So even in the space of just 1 second, I can look at 1 billion readings of the voltage. And that will explain, because if you have a fast enough MCU reading this signal, then it's going to be trouble for the MCU. And so I believe with what we have learned so far, if you sit behind a scope in the lab, you won't find it intimidating. You will actually enjoy it, and you will have fun with this all-important tool that makes engineers in other fields envy us. Go on tinkering, take risk, learn, and always remember that when it comes to electronics, doing teaches more than reading. Thank you very much. Until the next episode, bye bye.